Hello, Professor Sargent here with you again. We're going to take a look at applying information about the distribution of the sampling mean. In other words, the sampling distribution of X bar. The current book that I am teaching from, this is in section 8.1, and some important points to make are that we find out that if you take all the simple random samples of the same size, all simple random samples of the same size from a population, and find X bar for each of them, that the mean of all those X bars, you see it right here, that's going to equal the mean of the population, where you've added up all the individual scores, the X's, and divide by how many are in the population. So the mu of X bar is equal to the mu of the population. And the standard deviation of the sampling distribution of X bar will equal the original standard deviation, sigma, divided by square root of n. That is regardless of the shape of the population distribution. However, if it was in the population normally distributed to begin with, then we already have that sampling distribution of X bar will be normally distributed. Furthermore, the central limit theorem tells us that as you deal with increasing sample sizes, that regardless of the shape of the original distribution, eventually, with larger sample sizes, then the sampling distribution of X bar becomes approximately normal. And we look for that sample size to be at least as big as 30. Now let's start taking a look at some questions. All right, in this question, we are told that the reading speed of second grade students in a large city is approximately normal, with a mean of 90 words per minute and a standard deviation of 10 words per minute, or WPM for short. And although you cannot see it right now, at the top of every question from this publisher and with the online homework system, there is a question ID that goes along with the related problem at the end of the section in the textbook, but some of them have a dash T, which means when you see a dash T, they're expecting you to use technology. We don't have an option to open up table 5 for the normal distributions. So we're asked, what is the probability of a randomly selected student in the city that student will read more than 96 words per minute? We can use the normal CDF command. So let's see here. If you were to draw a picture to go along with this, talking about reading more than 95 words per minute. Sorry, 96 words per minute. You would have it marked at 96 and then shaded to the right of that. Well, it continues infinitely. You could find someone reading faster and faster. The TI-84 does not have a way of typing in infinity, so we put in the largest number that it can handle. Most of them is going to be 10 to the 99th power. Some of the newer ones may be 10 to the 999th power. So I will go to second and vars, because above vars is DISTR, short for distribution. I picked the second one, not the first one. My lower bound is the 96. The upper bound is the 10 to the 99th power. Mu is 90 and sigma was 10. I was working on a similar question with a face-to-face class recently. and they want that rounded to 4 decimal places. So the 5 in the 5th place is going to round that to 0.2743, rounding to the nearest 10,000ths. If 100 students were chosen, then by comparing this theoretical or classical approach to probability, and think about comparing that to an empirical probability, a relative frequency, I would expect dividing the number of students by 100 would give me about 2743. So if I reverse that, multiply the 0.2743 by 100, I'd get 27.43, but it doesn't make sense to have 0.43 of a student. That would round down to 27 students. And notice that we've got a few different ways to talk about what those 27 students would be doing. But since we were asked back here in the probability of reading more than 96 words per minute, it's going to be choice A. And there we go. What is the probability that a random sample of 10 second grade students from the city results in a mean reading rate of more than 96 words per minute? We're talking about X bar now. In the first question, we were talking about the individual scores within the population. Now we are talking about the sampling distribution of X bar. So real quick, if I'd done the previous question, first calculating a z-score by hand, and then going to the table, in the case with this textbook, table 5, I would have been using z equals x minus mu over sigma. But now in this part of the question, since we're talking about the sampling distribution of X bar, I'm going to have X bar minus mu, because mu of X bar is equal to the mu of the population, all over sigma divided by square root of n. You would want parentheses around the subtraction in the numerator and around the mini fraction in the denominator. That's going to change how we use the calculator. Okay, so you could go back to second and the vars to get into the distribution to call up normal CDF again. But this calculator lets me scroll back, copy and paste. So I'm about to do that and make a minor change, because we're still talking about reading more than 96 words per minute. So it's changing here when we have this dash T question, where we're expected to use technology, is that instead of sigma, we'll have sigma divided by square root of n. In this case, 10 is divided by square root of 10. Notice that how that got much lower. It's going to be more difficult to find a sample mean that is out in the extremes, out in the right-hand tail in this case, to get 10 of those children whose average as their reading speed being X bar being greater than 96. Harder to do that than it would be for an individual student. This is going to round again. If we want to go to 4 places, and we have an 8 in the 10,000th place, followed by another 8 in the 5th place. So that's going to round to 0.0289. And similar to the previous question, now if we had 100 independent samples, still with 10 students, multiply that by 100 and round. 2.89 would round up to 3, and we would expect that the X bar, on average, from those 100 independent samples of 10 students, that we would have X bar being greater than 96 in 3 of them. Greater than or more than 96 words per minute. All right, everything's working out okay so far. What is the probability that a random sample of 20 second grade students would have a mean reading rate of more than 96 words per minute? Instead of dividing the sigma, the standard deviation from the population that was 10, instead of dividing by square root of 10, now we're dividing by square root of 20. And now it's even less likely in a sample that's even larger. That's rounding to 0.0036. If I multiply that by 100, I'm only going to have 0.36, which would round to 0. We do expect with 100 of independent samples of 20 students that it'd be almost impossible to find a sample where they were reading more than 96 words per minute on average. What's happening as n increases, we look back at this formula here. As n increases, square root of n is also going to increase. So sigma divided by square root of n is going to get smaller. The whole fraction, dividing what you have from the subtraction in the numerator, dividing by something that's getting smaller and smaller, you're going to get an overall fraction that's larger and larger. Now, it could be negative, so I really mean the absolute values are going to be larger, which means we're talking about something either in the extreme left or extreme right-hand tail. And that's going to be less and less likely to occur. So as n increases, sigma of x bar is going to decrease. And let's see here. The probability decreases because sigma of x bar decreases as n increases. That looks like that's the one. Okay, yes it is. And I think we have just this one last part, maybe two. The teachers instituted a new reading program at school. After 10 weeks of the program, it was found that the mean reading speed of a random sample of 18 second grade students was 92.1. What might you conclude? Okay, well, let's treat it like the previous questions. 92.1 instead of 96, first of all. And second of all, sample size n is 18. I want to see if reading more than 92.1 would be something with a low probability, something where the score is extreme, so that we'd be talking about an unusual event. That is a relatively high probability. That would round to 0.1865. Which is not less than 0.05 or 15%. So it's not unusual. The probability was 0.1865. I think we had. Yes. Okay. 0.1865. That would mean that we could expect a mean reading rate, when we're talking about a simple random sample of 18 students. We should see that showing up. If we multiply this by 100 and then round, we would see that showing up in 19 out of every 100 random samples of size 18. And so This does not seem to be very unusual, and therefore not a program that is making a huge difference, apparently. Okay. I think this is the last part to this question. There's a 5% chance that the mean reading speed of a random sample of 22 second grade students will exceed what value? In this case, we are working backwards. If we had done those previous questions by hand, we would have calculated z-scores, then looked up in the table. So we would have gone from X bar to Z to a probability. Now they're giving us a probability or a proportion. Turn that 5% into 0.05. In the classical approach, you would have to find 0.05, i.e. 0.0500, or the closest thing to that within the table. Read backwards to find a z-score, and then do some algebra to find out the x bar. But since this is a -T, a technology question, then we need to use the opposite approach, the inverse norm, and we would use 0.05 for the area. The mean was it 90. Standard deviation was 10, and we are now dealing with a simple random sample of 22 students. So we would have 10 divided by square root of 22 for sigma. Now, in this case, my calculator has some more options than some of you might have, so I'll tell you what you can do in a moment. But we're talking about shading to the right because we want their mean reading speed to exceed that value. So stick with that, shading to the right. And that's telling me that it would need to be 93.506 something, rounded two places. So 93.51 words per minute. Okay, now before I go on to another, what if you don't have those choices? By the way, if your calculator is old enough where you didn't even get a menu for the normal CDF command, if it puts you right back in the home screen, then you'll be putting lower bound, upper bound, mean, and standard deviation. In the case of the sampling distribution of X bar, that would be sigma over square root of n, in that order. Lower bound, upper bound, mean, and then the standard deviation, considering whether you're dealing with a population or the sampling distribution of X bar. That's the order that that goes in. Okay, so similarly, you may not get a menu to type these things in. It may put you in the home screen. You need commas in between. That's right above the 7. You can't see the 7 on my screen most likely, but commas right above that. So by default, the older TIs, the TI-83 or an older TI-84 is only going to the left. And I want you to see something here. Yeah. Let's do that again. Let's change that to going to the left. Because of the symmetry of normal distributions. If I find out how far that score on the left is from the mean, and then add that amount to the mean, then I should get the same answer of the 93.506 something. Let's see. Let me just do this. Not that one. We just found out how far the one on the left would be. That would cut off the bottom 5%. Now we want to go the other direction. If my thing will respond. There we go. Okay. 90 plus that amount. And you can see we're getting the same answer there. See what other questions we have. Okay, here's the next one. Not a nice thing to think about. The acceptable level for insect filth in a certain food item is 5 insect fragments per 10 grams. A simple random sample of 50 10-gram portions of the food is obtained and results in a sample mean of X bar equals 5.7. We have a simple random sample of 50. They did not tell us that the population distribution was normal, but we have 50, which is greater than or equal to 30, so the sample size is large enough. The mean for the sampling distribution of X bar will equal the population mean. No rounding needed there. And the standard deviation will be the square root of 5 that we have for sigma divided by square root of 50. Because 50 is the sample size. So square root of 5 was the standard deviation for the population. And we're not dividing by 50, but by the square root of 50. And they want that rounded to 3 places. The thousandths place, that's going to be 0.316. So what is the probability that we would get a simple random sample of 50 of these? With at least 5.7. That's going to be shaded to the right again. When we say at least. So now we had a finite lower bound of 5.7. It would help to make a drawing there to make sense of that. You'd be shading to the right when you say the word at least. And then the shading would continue to the right. So we're going to have, whoops, sorry, not inverse normal. Normal CDF. So we're placing the finite lower bound of 92.1 with the 5.7. It keeps on going to the right. So I keep the 10 to the 99. Replacing the mean of 90 with a mean of 5 compared to the previous example. And I would be careful with taking the rounded version of the standard deviation of the sampling distribution of X bar. Sigma sub X bar being 0.316. You might get the answer, but I'm going to type in what I originally typed in. Excuse me, which was the square root of 5 divided by the square root of 50. And let it take care of that calculation. And rounding to 4 places, the 10,000ths place, that 2 right after the 4 would cause us to round down to 0.0134. This is smaller than 5% or 0.05. It is unusual because the probability is small, smaller than 5% or 0.05. And because the result is unusual, okay, X bar was 5.7. And so it seems that, relatively speaking, that's not a lot higher than the 5 that was claimed for the population. And so it would not be reasonable to reject that claim that it was higher than 5. Oh, sorry. Okay. Because it is unusual. Got something so extreme that makes me doubt that the mean of the population is really 5. Maybe it's higher. I don't know if it's actually the 5.7 that we get from the sample, but there seems to be some evidence that it is higher than 5. Here's a third question. The data in the table represents the ages of the winners of an award for the past 5 years. We want the mean. Get this to move. All right, let's do this. I'm going to open this up in Excel to get that average. Take a moment to open. Okay, here we go. So the mean for that small population of 5, typing in the 6th row, type equals the average of, oh, that was no good. Let's try that again. Equals average of what's in column A, row 1, down to column A, row 5. I also suspect that they want the standard deviation of the population. So equals STDEV. Notice that we've got 2 options here. And I'm going to go with .p. And I need to tell it that that also was for column A, row 1, down to column A, row 5. Now I may revise that shortly, but let's see what they're asking for. And what they're telling us, I believe that's meant to be a small population of 5. Okay, they are talking about a population, small population of 5. We had that the mean was 53 and 6.9857 approximately. So let's see here, 53. Okay, that's good. Okay, for those of you that have dealt with section 5.5 in this textbook, or if you're using a different textbook, then you would, if you have learned about the multiplication principle of counting, about factorials, permutations, and combinations, you can see that from a small population of 5, that there would be 10 samples of size 2. 56 and 45, those are 11 apart. Halfway in between would be 5.5, so our sample mean would be 50.5. 45 and 46 are only 1 apart, so 45.5. 56 and 54 are 2 apart. Halfway in between is 55. These are 19 apart, so 9.5. 10 apart, halfway in between, 5 more than 46 or 5 less than 56. These are 8 apart, halfway in between. 50 is 4 apart from each of those. And this is all stuff that you can be putting in the calculator, add the 2 and divide by 2. These are 8 apart. 10 apart. 9 apart. And 18 apart. See how I did. Construct a sampling distribution for the mean by listing all the sample means and their corresponding probabilities. Let me think for a moment here. I could be way off here, but let's try this. The first sample mean that I came up with was 55. That's showing up twice out of the 10. So 2 out of 10 or 0.2. The next one I came up with was sorry. Not sure about what order they want this in. So if I put the 50.5, that only showed up 1 time out of the 10. So 1/10, 0.1. Then we had the 55. That was showing up twice. $51 only showed up once. He's 60 only showed up once. Because there were 10 samples of size 2, I'm dividing all of those by 10. 49.5 only showed up once. Sixth one was 45.5. There's only one of those. Then we had 54.5. There's only one of those. Eighth one was a 50. There's only one of those. Ninth one was a 59. We're not seeing that anywhere. Now, I think since we've already accounted for 55, we want to put this. Instead of listing that again, we've counted the 2 of them here. So I'm putting N for no solution there. Not sure if that's what they want or not. $45.5, they've got a 0.1 like I do. 54.5, they've got a 0.1 like I do. 49.5, they've got a 0.1 like I do. 55, is that my error? 55, they've got a 0.2. Okay, so another issue, I neglected the directions here where we were supposed to be going up. But also where I had the 0.2. Well, I did have that part right. Okay, so it wasn't in ascending order. That's definitely a problem. If I add up all 10 of these, then we've got 45.5 plus 49.5 plus 50 plus 50.5 plus 51. Oh, 0.5 plus 51 plus 54.5. And then I'm going to put twice the 55. I could either add 2 copies or just do that multiplication. And then 59 was 0.1. And 60 was 0.1. Those of you that have dealt with chapter 6 in this textbook or have learned about finding the mean of a discrete random variable. I could have multiplied each of these by the probabilities. In my case, the way I did this, I have to divide by 10. I'll get 53 when I do that. Checking that I added correctly. Well, the mean of the population was 53. So the mean for the sampling distribution of X bar is also 53. So what's the probability the sample mean is within 2 years of the population mean age? So from 51 to 55, got 0.1, another 0.1, and 0.2. Adding those up, I would have 0.4. Okay, let's see what's left to do. Should just be one more example. Here, let's try this out. Game of roulette, we have 38 slots, 0, 0, 0, and then every integer from 1 to 36. Ball falls into the slots with that matches the number you selected, you win $35. Otherwise, you lose $1. Okay, let's see here. You're only picking one number. So you should only be winning if these are equally likely. 1 out of 38 times, they want us to round to 4 places. So 0.0263, 0263, and should just be a matter of 1 minus that answer. Let's double check that. 1 minus 0.0263. Okay, 37 over 38 when rounding to 4 places would round to the same place. 0.9737. Being in the standard deviation. Okay. This would be the mean would be 35 times the 1 over 38. So 35/38 plus the -1 score. So I'm taking score times probability of that score. Can't get to my negative sign here, so I'm gonna work around that. That was happening 37 out of 38 times. Now they may want us to have used the rounded stuff, but let's see what happens. Round to the nearest penny. So that would round down. I would expect on average to lose 5 cents. The standard deviation. All right, let's see here. I'm gonna do this in a table. So we take our scores. The probabilities. And give me a moment, got to remember how to do standard deviation for the discrete variables. All right, I have to admit I temporarily forgot, although I think I was close to the first formula with what I had in my mind. All right, so we found a mean of negative 0.05. So let's take those scores, x's, and square them. Scores minus the mean. Now we're subtracting a negative 0.05, which is going to be the same as adding 0.05. So I'll add 0.05 positive to each x, square it, and multiply by the probability. So I went to the top of the column and pressed enter. Score in list 1 minus a negative 0.05. Again, I can't get to my negative. It's going to have the same effect as adding 0.05 positive. I could have done this all at once, but I'm going to square those and multiply by the probability. So going to the top of that column, tell it to take what's in list 3 and square it. Put parentheses around this just in case. Square it, and then multiply by the probability from list 2. We then want the sum. Notice what we're seeing written here is not as detailed as what's showing at the very bottom. So I'm going to let the calculator find the sum of list 4. And then I still need to take the square root of that. Oh, don't want to do that. Let's get to the home screen. Second and stat. Math submenu. Sum of list 4. Take the square root of that answer. And they said to the nearest penny, so to the nearest hundredth, that would go to 5.76. See how I did there. Okay. Suppose you play the game 90 times, i.e. we've got a sample size little n of 90. Regardless of, in fact, that distribution is skewed. -1, there's only 2 scores, showing up a lot more often with a score of losing the $1. So this is skewed left. But we have a sample size of 90, which is greater than or equal to 30. So approximately normal for the sampling distribution of X bar, not the population. The mean is going to be the same as for the population. Then I'm going to divide by square root of 90. Take what I had for the standard deviation for a single game, divide by square root of 90. Notice how I'm using the most exact version the calculator could give me instead of the rounded, just in case. To the nearest penny, that would be 0.61. See if they agree with that. Okay. So what is the probability of being ahead after the 90 games? So the probability of X bar being greater than 0, that you have some amount of profit instead of a loss. Okay. So since this is dash T technology, instead of using z-scores in the table, X bar greater than 0 are shadings to the right. Start with 0 as a finite lower bound and 10 to the 99 as an infinite upper bound. Mean of negative 0.05. And standard deviation. I'm going to use my previous answer instead of the rounded version, and let's see what happens. Okay, can't get to it. 0.61 then. Oops. That. Clear that out. 0.61. Hopefully it'll be okay to use the rounded version. Not even 50% of the time. 0.5. It's less than that. Not by much though. Rounded to 4 places. 0.4673. There's one more 3 after the 3 I'm talking about, and that would round it down. So again, 0.4673. So what if we went up to 270 games? Okay. Well, sigma was originally 5.76. And now, talking about n being 270. Let's look at n again. 5.76. 5.76. Just leave everything else the same. Now divide by the square roots of 270. Checking that before I press enter. Yep, play 270 times. It's gone down. That 8's going to round the 2 up, 0.4433. Yep. So the more you play, the more likely you are to, on average, be losing. I think we'll see that showing up even more when we replace the 270 with the 900 in this parts. I was down to 0.3973 when we play the game 900 times. So the probability of being ahead, that you're making a profit, that X bar is greater than 0, it's decreasing as the number of games increases. Okay, that should be everything that I've got for now. All right, yes, it is. So Professor Sargent signing off. Stay safe and healthy, and hopefully I'll see you in another video.